Hello, and welcome back to the LinuxKI Toolset video series. In part 5 of this series, we will be exploring the LinuxKI PID Analysis Report, also called the KI PID Report. The PID Analysis Report builds on the LinuxKI trace data discussed in the prior session and provides detailed information for each task on the system. The PID Analysis Report helps answer the following questions on each task. When it's running, what's it doing? And when it's waiting, what's it waiting on? Recall from earlier sessions that the LinuxKI script is used to produce a LinuxKI trace dump, which is packaged into a gzip tar file along with the configuration data and other supplemental files. The KI all script is then used to extract the files and produce a set of default reports. The ASCII trace file was discussed in part 4 of this series. With the exception of the kparse HTML-based report, the remaining files are simply text-based files and can be viewed using a common text editor or viewer such as VI. In this session, we will focus on the PID Analysis Report. The PID Analysis Report can be located in the file KIPID, followed by the timestamp and the .txt extension. Each PID or task has a variety of sections or subreports, which describe different details about the task, such as CPU usage, wait states, system calls, I/O, and much more. We will discuss each of these sections in more detail later. After executing the KI all script to extract the data and generate the reports, the LinuxKI reports can be found in the files with the .txt extension. The PID analysis report will be in the .txt file starting with KIPID. We will use VI to open the text file and view the data. Note the first line in each text-based report will contain the KI info command that can be used to generate the report outside of the KI all script. The first section for each PID is the scheduler activity report. You can find detailed statistics such as how much time the task spent running, both in user code and in kernel code, sleeping, and waiting for CPU. This section includes information on how interrupts impact the task, information on CPU and NUMA node migrations, as well as some memory details. The CPU MSR report provides advanced CPU metrics. The metrics can provide details on efficiency of the CPU, such as the last level cache hit rate, cycles per instruction, or CPI, and the average CPU frequency in megahertz. Note that these metrics are only available on physical servers and collected with the LinuxKI script using the -R option using the LinuxKI DLKM module. The PID RunQ latency report provides detailed information on the CPU wait times. The cooperating competing task report provides information on other tasks woken up by the task being analyzed, as well as information on other tasks that wake up the task being analyzed. These statistics can be helpful to see how the various tasks either cooperate or compete for resources. The sleep report provides detailed information on the wait states. This report can help answer the question, when it's waiting, what's it waiting on? The first section provides a summary of the kernel functions where the task went to sleep. In this example, we can see that the task spent over 12 seconds waiting for one or more mutexes and over 5 seconds waiting for I/O. The sleep stack traces provides a sort of call graph of the stack traces which show the code paths leading up to the sleep. Note that the stack trace includes both the kernel stack trace as well as the user stack trace. The RunQ stack traces represent the stack traces when the process is preempted. Often, the RunQ stack traces provide details on the busier kernel functions and user functions. The CPU activity report provides CPU profiling statistics for the task. Approximately every 10 milliseconds, the instruction pointer and the stack traces are recorded as a hard clock trace event. These events help answer the question, when it's running, what's it doing? We can use this information to identify hot functions and stack traces for the task. The system call report shows each system call made by the task, how much time it spent on each system call, and how much of that time was spent executing on the CPU, waiting for CPU, or sleeping, along with the sleep functions where the system call went to sleep. The file activity report will split out the system calls based on the files being accessed, so we can tell which files the task spends most of its time on. In this case, the task is only accessing a single file called big file. We can also see the mutex locks contention occurs on both the write and the lseek system calls, while the write system call also waits for I/O. Remember the cooperating and competing task report? It's a good bet that the other tasks mentioned there are competing for the same mutex lock. Finally, we get detailed statistics on the physical I/O performed by the task. Note the statistics for each device are split into reads and writes, and reads plus writes, or total. There are statistics for both the SCSI block devices and the multipath block devices if they're used. In this case, the multipath block device has 8 I/O paths. If you need additional information on LinuxKI and the PID Analysis Report, be sure to check out the LinuxKI Masterclass documentation on the LinuxKI wiki page. Thank you for joining and have a great day.